Hello everyone, and welcome to the second instructional video on Virp charts. This one we're going to focus on parallel. So you should definitely watch the first video first, obviously, because I'm going to skip through some of the explanations that I had at the beginning of the one on series. On parallel, we're just going to dive right in. So the first thing we're going to have to do, again, is we need that total resistance. So since it's a parallel circuit, we have to do equivalent resistance 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. So we have 20, 20, and 30. Common denominator. You can use a calculator. This is a little bit of overachieving, but whatever. 3, 3, and 2 is 8, so 8 over 60. Now, what that tells you again is 1 over R equivalent equals 8 over 60. So, effectively cross multiplying, or what cross multiplying is really doing is you're taking your numerators and denominators and you're flipping them. So, R equivalent equals 60 over 8, which is 7.5 amps. So I'm going to go here, 7.5. What I'm going to do is I'm going to actually delete all of this stuff here on the resistance. If you need to still take a look at that mathematics, obviously pause the video and help yourself, but I'm going to delete it to clear myself some space. Now I'm going to move on to P equals IV. For this particular column, since I have 2 items in the column, I can finish off that column. So I'm going to use V equals IR and P equals IV. We got 120 equals I times 7.5. On the calculator, that will tell us if I divide both sides by 7.5, I am left with 16 amps. So this will be 16, and then the power will be 16 by 120. So 16 by 120 is 1920 watts. So in the series circuit, our next step was to say, all right, well, I just saw 16 amps has left the battery. So the 16 amps is going, but then I reach this intersection here. And that's a problem because I can't say how many amps go to R1 and how many continue on to R2 and 3. Now I can build ratios of it, but these resistances are not equal. So I have a 20, a 20, and a 30. The two 20s are going to get more current than the 30 because the 30 has higher resistance. So we can't do current to solve this like we did last time. Instead, what we're going to do is we're going to do voltage. Now voltage, the way voltage works is voltage doesn't actually split across the lines. So what's happening for voltage is, I have 120 volts from the power source. This entire line sits at 120 volts. It doesn't split at all. It's established across the entire line. The only thing that can raise voltage is a battery or power source, say a wall outlet, and the only thing that can remove voltage is a resistor. Now, I always return to the battery at 0 volts, which means this last remaining line that connects to the negative terminal of the battery sits at 0 volts. You could say, well, why does it have to be 0? Well, it honestly doesn't have to be. This was a 120 volt power source, so the only thing that really mattered was the difference between this red line and this blue line is it has to be 120 volts. It could be 240 and 120. Voltage is technically a relative term, but to make life easy, it makes sense to us to say, well, let's make the final return line 0 volts because I've expelled all of the potential in the circuit. Now, our next step is to say, well, all right, R1 bridges a gap of 120 to 0, R2 bridges a gap of 120 to 0, R3 bridges a gap of 120 to 0. So Rs 1, 2, and 3 are each consuming 120 volts. Now you may think, well, that doesn't seem right. It just tripled the amount of power, but it didn't. And we'll get to power in a moment, because the thing that we're not accounting for in power is there's also current. The voltage is just the potential. You still need current for the total power. All right. Once again, I have 2 in a column, 2 in a column, 2 in a column. So I'm going to finish off these columns. V equals IR, so 120 equals I times 20. $120 is I times 20. I will turn out to be 6 amps, 120 and 20, 6 amps, 120 and 30, 4 amps. Now power, final row, let's go orange. 120 by 6 is 720. 120 by 6 is 720. 120 by 4 is 480. So here is my power consumed. 720 plus 720 plus 480. I got 1920, which means my 3 resistors consume 1920 watts, and my power source generated 1920 watts, so energy is conserved. What's happening is, since the battery or power source or whatever you want to call this is pumping out the 120 volts for the whole line, it has to pump out triple the normal amount of current, or not necessarily triple because this resistor is 30 as opposed to 20, but it has to pump out more additional current, and therefore the result is your battery is going to be expelling its energy faster. All right, folks, take a look at numbers 5 and 6. Enjoy.